In this video, we're going to talk about hypothesis testing. Now, before we get into what hypothesis testing actually is, I want to pose a question. All right, so let's say that you work for a lumber company, and this company has developed a new way to grow pine trees that is twice as fast as normal. This company is doing so to convert those pine trees into lumber used for construction, 2x4s, things of that nature. All right, the question they want you to answer is, are these 2x4s made from this new type of pine tree, are they strong enough to be used in construction, right? Will they hold up to the kind of weight? Will they be able to hold up a building, right? So how would we test this? How would we know that that's the case, right? The answer, probably unsurprisingly, is hypothesis testing. Right? Hypothesis testing is the way we answer questions about population parameters using sample data. And this is a very important tool, not just in statistics or business statistics, but any kind of science that you would be doing. All right, perhaps more important for things that are social sciences. But it is very important because most of the time we're wanting to know something general about a population parameter, right? But in order for us to actually find that answer, we would have to gather all the population data and calculate whatever answer we're looking for. And most of the time we don't really want to do that for a variety of reasons, right? Population data is more expensive to collect, it takes more time to collect, and sometimes it's just not possible to collect all of the population data, so we have to rely on samples. Right? This allows us to take that data we get from our samples and make inferences about the population, right? This is inferential statistics. This is where we really start getting into it. We've been kind of getting into it, but this is where it really kicks off. All right, one last thing I want to note before we really dive into this is we are going to be making an analogy throughout this video / videos. Right? We can kind of think of hypothesis testing like a criminal court case. So that's going to be an analogy that we come back to time and time again as we go through the process of hypothesis testing. Right? Speaking of which, let's go ahead and talk about, just in an overview, the actual process. All right, so in your book, there are 10 steps for hypothesis testing. I personally believe that's way too many steps, so I'm going to cut it down to 5. So in your book, you're going to have 10. Per this lecture, there are 5 steps for hypothesis testing. Really, we're just combining some things, or I'm combining some things that they broke into different steps, leaving some things out, but it's going to give you the same result. All right, so let's look at our 5 steps for hypothesis testing. All right, our first step is to state the hypothesis. All right, we need to state our hypothesis. We're going to just speed through these and then we'll go into them in more detail one by one. All right, so state the hypothesis. The next step is we need to specify the significance level. Third, we need to determine the critical value. Four, we need to calculate the test statistic. And the fifth and final step of hypothesis testing is that we need to reach and state our conclusion. Before we begin looking at these individually, I'm going to stress, and I will stress this later on, a full, complete hypothesis test requires you to go through all 5 steps. If you only go through the first 3, it's not a complete hypothesis test. If you only go through the first 4, right, it's not a complete hypothesis test. All right, all elements, right, have to be present for it to actually be a complete hypothesis test. All right, but enough about that. Let's start looking at these steps. All right, so the first step, state the hypotheses. All right, and that is correct. It does say hypotheses, all right? And the reason for that is because when we're doing hypothesis testing, we're gonna have 2 hypotheses, all right? The first hypothesis is what's known as the null hypothesis. Alright, so the short version of what the null hypothesis is, this is the claim that we are going to assume is true until we can prove otherwise. Alright, I guess that's not really the short version, that is the full version, right? So it's the claim that we're going to assume is true until proven otherwise. And it's going to be notated H with a subscript O, right? So the null hypothesis, H subscript 0, we sometimes refer to that as H naught, all right? So either the null hypothesis or H naught, that is the claim that we're going to assume is true until proven otherwise. Right. The other hypothesis that we're going to have to state is what's known as the alternative hypothesis. Right now, in most cases, the alternative hypothesis is the claim you are trying to prove. All right, that's not always the case. We're going to talk about that in a little bit more detail in just a moment. But for the most part, the alternative hypothesis is what you're trying to prove. And it is going to be notated as H with a subscript 1. Now your book and other sources notate this as H subscript A for alternative. However, I learned it using H1, so that's what we're going to use in this class. If you use HA, that's absolutely fine. If that's going to make more sense to you, use that. H1 and HA, they are the exact same thing, all right? But I'm going to be using H1 on the board. All right, so I said that we're going to be using an analogy of hypothesis testing being similar to a criminal court trial. All right, so that's where we're gonna start looking at that right now with our hypotheses. So if we're talking about a criminal court trial, there is something that we assume to be true until it's proven otherwise, right? And that is, we are going to assume innocence. Right, so H naught would be not guilty, that the person is not guilty, right? In hypothesis testing, we kind of take on the role of the prosecution, right? And our claim is that the defendant is guilty. So that's the alternative hypothesis. All right, so the burden of proof is on us as researchers, right? We have to prove, right, that the null hypothesis is incorrect. And if the null hypothesis is incorrect, then the alternative has to be true, right? Because just like this with not guilty and guilty, right, it has to be one or the other. We're gonna set up our hypotheses in such a way that it has to be, the truth has to be one or the other, either the null hypothesis or the alternative hypothesis. We're not always gonna know which one, but it's going to be kind of a binary decision at that point. All right, so that's what that might look like if we were to create a null and alternative hypothesis for a court case. But let's look at what they look like for this class, right? Because we're not going to just have words, right? We're going to be putting these in mathematical notation. All right, so what this chapter is focusing on is hypothesis testing of the population mean. So that's what all of our stuff is going to be about, right? Questions about the population mean. So just setting that up so you know that you're going to see that mu symbol quite a lot. Right, there are two overarching types of hypothesis tests, one of which has two subtypes. So let's go ahead and look at how these tests might be set up. We already know we have a null and an alternative hypothesis, but there's definitely more to hypothesis testing than that. So without further ado, the first type we're going to talk about is what are known as two-tailed tests, right? Or a two-tailed test. We'll talk about why it's called a two-tailed test later on in the chapter, but for now we're just going to focus on the hypotheses. All right, so the null and alternative hypotheses for a two-tailed test are going to take this form. All right, so the null hypothesis, H naught, is that mu equals C. Now C is an arbitrary constant. Some places will call it the hypothesized mean, but that's going to crop up in a lot of other places, so I like just use C. It's the arbitrary constant. It's whatever we're comparing that mean to. All right, so that's going to come through the problem that we are given. All right, we'll see that. We're going to do some examples. We'll see where that comes from. All right, but this is an arbitrary constant. It's not arbitrary in that it doesn't have any reasoning behind why you choose that number, but you are just you're going to choose that number for whatever reason, right? There may be some benchmark that you're going to be comparing the population mean to, something else along those lines, right? But it doesn't have a calculation that we're going to need to do to get that C, right? Then the alternative hypothesis is going to be mu does not equal C. All right, so when we are kind of faced with a two-tailed test, we're going to get things like, test the hypothesis that this is not the same as that, right? Or test that this is different from that, something along those lines, right? There's no direction implied with a two-tailed test. You don't care if the mean is greater than your arbitrary constant or less than specifically, right? Just different. So it could be greater than, less than, you don't care, you don't have any directional kind of idea for that. All right, so one last thing I want to note on the two-tailed test. So earlier when we were talking about the alternative hypothesis, I said that it's almost always the claim we're trying to prove. When we're dealing with a two-tailed test, that's not always the case, right? Sometimes it is, sometimes it isn't, right? And the reason for this is partially just because the way people phrase questions, including myself, right, and kind of the properties of hypothesis testing in general. All right, if I were to phrase a question as test the hypothesis that the mean of whatever does not equal 52, all right, then you could go up and your alternative hypothesis would be mu does not equal 52, all right, and that would be fine. But I might also phrase it as test the hypothesis that the mean equals 52, right? Two different ways of phrasing that question, but it's still the same test, right? And if in the second phrasing where I say test the hypothesis that the mean equals 52, you would not want to put mu equals 52 as your alternative hypothesis, right? We always want the equal sign to be in the null and the does not equal to be in the alternative. All right, the reason for this has to do with, I think in philosophy, it's often called the problem of induction or something along those lines, right? But basically it comes down to this, right? Kind of the idea is that which of these two phrases is easier to prove, right? The first phrase being all crows are black, and the second phrase being not all crows are black. All right, so you have two statements there, kind of getting at the same thing, right? But the way you would go about testing these is very different, right? For the first one, where we're saying all crows are black, right, we're trying to prove an absolute. So what we would have to do in order to actually prove that would be collect all the crows in the world and make sure every single one of them is black, right? That's a very daunting task, right? On the other hand, if we're trying to prove the claim that not all crows are black, we don't have to collect all the crows in the entire world. All we have to do is collect crows until we find one non-black crow, right? And it's going to be much easier to find, a single albino crow than it is to find every single crow in the world, right? So we never want to try to prove an absolute, right? Never want to try to prove a mu equals something statement, because it's impossible. We're not going to be able to do it. Well, it's not impossible in all cases, but it's very difficult and it's not worth the effort, right? It's easier to just get that sample, all right, and do it the other way, all right? So all of that rambling to say, right, when you're doing a two-tailed test, it has to look like this. The only thing that should change is your arbitrary constant as far as your null and alternative hypotheses go. Mu equals C in the null hypothesis, mu does not equal C in the null, or in the alternative, right? So that's the way we have to have that set up. Right now, the next type, what are known as one-tailed tests. Right? These are split up into two types. All right, we have right-tailed tests and left-tailed tests. All right, so for our left-tailed tests, we're going to use these when we're asking questions like, what is, test the hypothesis that the population mean of whatever is less than blank, right? Test the hypothesis that the average number of some things is fewer than blank, right? So that less than, right? That less than connotation, right? Words with that less than connotation, right? Saying that we think the population mean is lower than whatever our arbitrary constant is. All right, so when we're doing one of these left-tailed tests, our null hypothesis will be that mu is greater than or equal to our arbitrary constant. All right, and our alternative hypothesis is that mu is less than the arbitrary constant. All right, one thing that I'll note, and we'll see this when we start doing some examples, it's usually easier, especially when we first start, to write the alternative hypothesis first, because again, it usually, in most cases, it's going to be the claim that we're trying to prove. All right, so we can easily get that alternative hypothesis, get that down, and then make the null the opposite of what it is, right? One of the reasons is because, right, if the alternative is the claim we're actually making, that's what's going to be in the problem that you get on a homework or a test. All right, also, if we can't remember left from right-tailed test, right, it's handy because the inequality symbol in the left-tailed test, right, points to the left. All right. The same is true in concept for right-tailed test as well. All right. Well, we'll look at that right now. So that's our left-tailed. Our right-tailed, as you could probably imagine, this is when we believe our population mean is greater than that arbitrary constant. Right. So when we think, testing to see if the population mean is more than some value, greater than some value, so on and so forth. All right, so mu less than or equal to C will be our null hypothesis for a right-tailed test. Mu greater than C will be our alternative hypothesis for a right-tailed test. Right, and once again, we see that inequality symbol pointing to the right. All right, so right-tailed test points to the right, left-tailed test points to the left, right? Of course, that's for the alternative hypotheses. All right, so again, these one-tailed tests I think are easier to set up because they're a little bit more straightforward, because you can pretty much guarantee that whatever the prompt is telling you to test for, that's what the alternative hypothesis is. You don't have to worry about switching anything around, doing anything like that. When we do the two-tailed, of course, you need to keep in mind that that does not equal to, needs to be in the alternative hypothesis. So even if we're being asked to prove that or test that something equals some value, we need to have mu does not equal that value in our alternative. All right, so let's look at some examples. All right, so I got 3 examples. I'm gonna just read them out, and then I'll pause for a few moments, and then we'll go over them, right? So if you wanna try to stop and figure that out, I'm not gonna pause long enough for you to do it, so just pause the video, and then whenever you're ready, you can go ahead and hit it and see if you got these right. All right, so I'm just gonna read these out. I'll go ahead and read them out twice, then I'll wait for a moment, and then we'll see if we got them. All right, so here's the first one. All right, you believe that the average Calhoun student has a commute of less than 20 minutes. You believe that the average Calhoun student has a commute of less than 20 minutes. All right, so we'll pause. I'll just keep kind of rambling for a little bit as we mull this over. Hopefully you're not trying to do this while I'm talking. Hopefully you muted the video, otherwise this would be really distracting. All right, but I think that's probably long enough to give people time to pause the video if they wanted to. So let's look at the answer. All right, so when we're looking at this, there's really 2 key pieces we need to know, all right? Because when we set up our null and alternative hypotheses, right? These first two parts are already guaranteed. All right, that looks the same for two-tailed, right-tailed, left-tailed for all the tests, right? So what we need to know is, are we saying that the population mean is greater than or less than some value, and what is that value? What is that arbitrary constant we're looking for? All right, so again, this one's pretty straightforward. We're gonna start with the alternative because again, that's usually what's in the problem. So, and that's the claim we're trying to prove. So it's usually the easiest thing to kind of figure out. And then once we have that, we can get that null hypothesis by just making it the opposite of our alternative. All right, so we're reading this, all right, we're saying you believe that the average Calhoun student has a commute of less than 20 minutes, right? So those last couple of words, less than 20 minutes, right? We're saying that the population mean for commute is less than 20, all right? Less than obviously says it right there, it gives us that inequality, and then 20, all right, that's our arbitrary constant. All right, since our alternative hypothesis is mu less than 20, all right, then the null hypothesis has to be mu less than or equal, greater than or equal, all right? It's because we want it to be the opposite. So this should be mu greater than or equal to 20. All right, so hopefully we got that, or we understand where we went wrong. And let's go ahead and move on to the next one. All right, so the next one says, you believe the average family spends more than $250 on groceries per week. All right, once again, you believe the average family spends more than $250 on groceries per week. All right, so once again, I'm gonna kind of ramble a little bit, let you have time to pause the video or try to figure it out. You know, depending on, some of you might just be able to write it down in the time it takes me to kind of ramble through. Again, this is probably really distracting, so if you can do it under these conditions after just having learned about it, that's pretty impressive. All right, I think that's enough stalling. Anybody that wanted to pause the video and take a crack at it has had time, so let's go ahead and look at it. All right, so once again, setting these up, the first little bit is going to be the same, right, as it is for any of the other stuff, right? Then we need to, so we're gonna focus on our alternative hypothesis, right? So what is the claim we're making, all right? Average family spends more than $250 per week on groceries, right? So we're saying that the population mean for our variable, which is kind of grocery expenditures, right? That the population mean is greater than 250. All right, so greater than, that's telling us it's a right-tailed test. The 250, it's the only number in the problem, so that's probably our arbitrary constant. So our alternative hypothesis would be that mu is greater than 250, right? Then to get our null hypothesis, we'll just make it the opposite of our alternative. So if mu greater than 250 is our alternative, then our null needs to be mu less than or equal to 250. All right, so that is our null and alternative hypothesis for this one. All right, now for the last one. All right, it says you believe the average temperature in Antarctica does not equal negative 300, or excuse me, ooh, that'd be rough. I mean, it's negative 30 degrees Fahrenheit, so it's still pretty dang rough, but I feel like you would just die if it was negative 300. Regardless, all right, here it is again. All right, you believe the average temperature in Antarctica does not equal negative 30 degrees Fahrenheit. All right, so once again, we're just going to kind of stall, really, I guess, make this video a little bit longer for some reason. Yeah, so if we want to stop and have a go at it, we need to do that now because we're about to start answering it. once again, all right, we can go ahead and put up this first little part because that's not going to change. We could just do these one at a time. That's not going to make a difference, but now we got to figure out what our alternative hypothesis is. All right, so the question says you believe the average temperature in Antarctica does not equal negative 30 degrees Fahrenheit. All right, so we look at this, all right, we don't have any indication of one direction or the other, nothing telling us that we think the population mean is greater than or less than some value. We're just saying that it's not the same, it's different, right? So that's going to tell us that this is a two-tailed test, right? Now, when we go to make our alternative hypothesis, we know that we need the does not equal in that alternative hypothesis for two reasons. One, I told you that it has to be, all right? You should never have equals in the alternative hypothesis, all right? So that's one reason. The second reason is because this one was kind of easier and it straight up said temperature in Antarctica does not equal. So does not equal, that is exactly what we're looking for that alternative hypothesis, right? So it does not equal negative 30 degrees Fahrenheit. It's a safe bet that negative 30 degrees is that negative 30 is our arbitrary constant. All right, so our alternative hypothesis would be that mu equals negative 30. And to get our null hypothesis, we just need to find the opposite of that statement. So mu equals negative 30, right? And that would be our null and alternative hypotheses. All right, so we're gonna go ahead and end this video here. In the next video, we're gonna just pick up right where we left off. We're gonna jump into the second step of hypothesis testing, which is talking about specifying the significance level. All right, so I will see you in the next video.